for today.
Well, thank you very much, Tommy. Yes, my name's Jim Rickles. I'm the director of the NHERI Lehigh facility. We specialize in cyber physical simulation in terms of structural testing, and I think the topic today is very well suited in terms of relating the two aspects of that. But I'm actually joined by, as Tommy already introduced himself, he's one of two research scientists. The other is Leanne Kell, who's also with us, and Claudia Reich, Professor Reich. She's a co-principal investigator of our facility. Now, we're sponsored by the National Science Foundation. We're a shared use open facility. And if you need to, and I encourage you actually to inquire about more information, you can go to our website by just Googling NHERI, N-H-E-R-I, and perhaps then Lehigh, and you can find a lot of information about our facility. So the purpose of this seminar, it's part of a series, and the purpose of the series is to create an awareness and opportunities for you to learn about some evolving and hot topics, and also for the presenters to create an awareness of their research. So with that, let me introduce the speaker. The speaker is Professor Eleni Chatzi. She's the chair of the Structural Mechanics and Monitoring at the Institute of Structural Engineering within the Department of Civil, Environmental, and Geomatic Engineering at ETH in Zürich. Currently, she's the president of the European Academy of Wind Energy, and she has a number of research interests, but amongst them is the field of structural health monitoring, in particular hybrid modeling for digital twinning and data-driven decision support for engineered systems. And as a result of that, she's got a number of grants and also recognition. One of these is a self-aware infrastructure that the domain of that has been recognized by the ERC starting grant. It's won the 2020 ASCE Huber Research Prize, as well as the 2020 EASD Junior Research Prize within the area of computational structural dynamics. And then furthermore, the J.M. Koo Award and the 2024 Structural Health Monitoring Person of the Year Award. So without further ado, I'm going to hand the microphone over to you, Eleni, and welcome to today's seminar.
Thank you very much for this introduction. I'm Eleni Chatzi. As mentioned, I'm faculty at the Department of Civil Engineering at ETH Zurich, and I would like to present a bit on what we do there with the group in the domain that was already mentioned, which has to do with structural health monitoring, but let's say from a perspective that is focused also on the aspect of modeling. And indeed, this is the way in which we perceive SHM in our group. SHM, short for structural health monitoring. It's we see it as the principle of gathering information from actual operating systems in most cases. And here we have today the possibility to extract diverse and heterogeneous amounts of data, even from large-scale structures, such as the ones we're usually interested in the domain of civil engineering, which can come in various forms. And what we would like to be able to do with this kind of information, which is raw in its initial nature, is to be able to process it in a way that is indicative of the current condition of the system as is, which is the task of diagnosis, as well as the forecasting as the future or remaining useful life of the system, or the performance of the system under different and various types of loadings that are maybe not yet experienced, which is the task of prognosis. And we perceive the linkage between raw information and this kind of interpretable indicators to be easier, let's say, extracted more easily with use of simulation models or by fusing engineering knowledge in the loop. And we typically do this by using principle of mechanics and dynamics. We do this not only for the individual structural level, the individual asset level, but also for assemblies or fleets or populations, as you may hear of it, of assets. For example, you can imagine the different structures that comprise the roadway networks, be this tunnels, bridges, the roads themselves, and so forth. Or, for example, assemblies of similar structures such as wind turbines as you would meet them within a wind farm. So we're interested in translating this information also at that level. And I will be focusing here on what is the main strength for us in doing so, which is the aspect of simulation. But before I discuss simulation, I think it also makes sense to explain what we can today do purely on the basis of data. And in fact, there is a lot that we can do with data. And I already mentioned that there's many ways in which we can today derive such information. And I show you here some of the domains within which our chair is currently active, starting from the domain of mobile or indirect monitoring, where we extract data from vehicles that are appropriately instrumented in order to understand the condition of the traversed infrastructure. We're also heavily active in the domain of wind energy structures. For example, here you see a wind turbine facility that is owned by our chair, and we use it as a living lab to understand how these structures can be monitored and how they perform. But we also monitor more traditional pieces of infrastructure, of civil infrastructure, such as buildings, bridges, and of course, engineering assets, because there as well, condition monitoring is a prime instance of managing these components. So before I show you the aspect of physics-based simulation, I wanted to discuss a bit more what is the value of using data. And so for this, I'm using an example from monitoring of wind farm systems. Here we have rich amounts of information from what is known as SCADA information, which is visual information collected at the nacelle level for each one of these turbines on operational conditions, on the loads that they are experiencing, and so forth. That being said, this kind of rich availability of data can also enable us to infer physics information within this wind farm, such as, for example, the flow of the wind within the wind farm, which you see depicted here. And this is something that has arisen as a result of generative modeling, meaning that we have used the data to try and extract this type of information. And we further then try to translate it into information that is useful for the engineer, such as, for example, the wake deficit, which is an engineering quantity that can be used to reliably design these systems. It can also be translated into damage equivalent loads, which have to do with the fatigue that is experienced by these systems. But what we claim, having said that, is that data alone is not enough. Usually the models that we build in this way, purely coming from data, is only as good as the training set from which they have originated. And it's not easy to extrapolate this data. So we know that there are common pitfalls in data-driven modeling, and I don't have to explain this maybe in this crowd. This includes the fact that our generated models are often not interpretable because they're usually of black box nature. It's not easy to have a connection to a physics-based quantity, so we're lacking physics connotation. And it's not easy, as I mentioned before, to extrapolate to unseen data or, let's say, unseen loading situations. In a way, this resembles this kind of proverb of the six-blind man and an elephant, where you have different experts looking into very narrow domains, and what they experience can be very different and very far from the actual truth, purely on the basis of what it feels like they're actually seeing or experiencing. And so what we're saying is that physics, or our good old engineering knowledge, can be used as a positive inductive bias to broaden our learning experience and to somehow boost it towards the direction that is more informative. So when you want to move away from purely data-driven representations, where we know that data can excel, but actually are good enough only for diagnosis, the moment you want to move to the prognostic task, it's important to bring into account the extra knowledge onto the system, which can be represented by physics. So here we're trying to do this construct where we're merging physics together with data in what is known as hybrid models, meaning models that are merging the best of both worlds to be used for multiple tasks that can do both diagnosis and prognosis, tasks that are basically usually attributed to the so-called digital twins. And so this is what we're trying to do here, to construct these interactive digital twins that can bring this information into the loop and feasibly do this even as the data is unattained, which is what we refer to as real-time digital twins. And these kinds of constructs, they would have to actually operate under challenging conditions, both for nonlinear dynamical systems, as well as for varying environmental and operational loads. They have to be able to perform for distributed loads, and they have to be able to comply not only the information that is gathered from, let's say, balance the information that is coming from sparse sensors, but also the information that may be predicted from models that are usually expensive in nature, multi-degree of freedom models that we have to reduce in order to couple with the data. And there's a number of tasks that you can imagine you can do with these kinds of systems, including reduced order modeling for the purpose of visualizing these systems and digital twinning, hybrid simulation tasks that are very relevant for the context that we're here discussing as part of this group, general tasks about diagnosis, prognosis, and of course, control. So if you would like to, let's say, define this task, the way you could view it is basically as trying to deliver everything everywhere all at once. You can imagine having a structural system with sparse sensors, which has in itself is experiencing unknown or unmeasurable loads. We have usually a model of the system as engineers, which is not perfect. So it's maybe suffering due to imprecise information, such as wrong or unknown parameters. And we would like to predict the response of the system. Usually that's what you try to do for a digital twin for various engineering tasks. And you would like to do this under multiple uncertainties that describe the system. And physically, you would like to be able to extract the response of the system, not only in a single location, and certainly not in measured locations alone, but in the full field, as we say, so in the entire construct of our system. And now there are many difficulties that are hardening this task, including the presence of uncertainties, nonlinearities, the fact that we have sparse and limited observations, large dimensional systems, and the fact that we are usually also pressed for time, such as, for example, for early warning systems or hybrid simulation tasks. You want to be able to infer this prediction very, very fast, feasibly as data is obtained. So we're trying to solve this kind of a problem. And if we try to approach it with a classical structural mechanics approach, which is something we're very used to do as engineers, for example, in our group, we're developing different frameworks for complex analysis, such as fracture mechanics, hysteresis and plasticity, substructuring and large deformations. But these frameworks are, of course, very precise, oftentimes, but they require a large number of assumptions, and they're oftentimes very, very slow. So they will just not cut the real-time digital twinning concept. They have to be reduced in order to be able to work with our constructs. So one way to achieve this reduction is to try to do it in a surrogate modeling approach. In this kind of approach, we have a full order model of the system, and we can try to train a neural network in simulated data from the system, and then extract a latent representation, a feature space, which is enough to describe the dynamics. You can imagine in a linear system, this would, for example, be the model space of the system, and we can then extract a mapping of the forcing to the system with this latent representation, which means that we can solve or integrate an equation of motion that is equivalent in reduced coordinates. You can do this with any integrator you wish. In our case, we're using recurrent neural networks to do so. In other situations, we have used transformers. But what is important in this case is the fact that we're using an autoencoder kind of setup, which means that at any point of the analysis, we can use the decoder to go back into our original full order model, which means the original full degrees of freedom of the problem, which is really where the physical response lies. And we need to do this because we need to connect what we monitor with the actual coordinates of the problem. The latent space usually doesn't have a physical connotation, so it's not enough to be able to live in that feature space. So this kind of a framework is very nice. We have shown that it works also for experimental data for nonlinear problems, such as, for example, the very well-known benchmark by the Los Alamos National Laboratory. This is a nonlinear shear frame with a nonlinear element, a bumper on the third floor. We have analyzed the response data from the system, and we have developed this surrogate, which when decomposed, so when you look at the spectrum of the features that are extracted, you would see that you have isolated spectral properties. Even though it's a nonlinear system, it seems to be approximating the so-called nonlinear normal modes of the system. This is contrary to the naive or popular approach to this kind of decomposition that would, for example, be a PCA analysis, even if it is a nonlinear PCA, which would actually mix the spectral components. So by using a variational, actually, autoencoder in this case, we're favoring this decomposition that is meaningful, and we're trying to promote the solution of the system in its meaningful modal coordinates, let's say. We have implemented this problem also on a more realistic and large degree of freedom setting with our partners in Siemens Gamesa, who have given us simulations of wind turbine structures, specifically nonlinear simulations due to the monopile foundation, which is the nonlinear element here, that is, let's say, governed by these kinds of curves that are causing a behavior that is very time-consuming to actually solve. So we use this kind of reduced order model, which is based on the VAE approach, to give them a surrogate that is very, very fast to compute and actually gives them a precision that is very close to the one that they desire to have at the full field simulation of this nonlinear multi-degree of freedom system. It can be then used as a replacement. So we have a reduced order model, but the question is, how do we deal with the fact that we would need, in an ideal setting, to express this reduced order model in a parametric setting? We would like to be able to extract this prediction not only for one configuration, for example, of the foundations of the problem or the parameters of the load of the wind turbine, but for multiple such different parameters. Now, to do this, we have been following a slightly alternate approach. When we want to use parametric reduced order models, we try to use a framework that is closer to the physics of the problem. And to demonstrate this framework, I will show you a popular example from civil engineering applications, this kind of shear frame, which we also offer as a benchmark for the dynamics community, and especially the community that is working on reduced order representations. So this kind of benchmark structure is basically a nonlinear frame where the nodes are governed by nonlinear springs, specifically hysteretic Book-Wen type model springs that you see here, governed by this model. Each and every one of these joints is a separate such spring. And we're here trying to parameterize this model by looking into two sets of parameters. One that is actually representing the ground motion characteristics in the spectral and temporal domain, and another set that is representing the parameters of the frame in terms of the elastic properties, the Young's modulus, but also parameters of the nonlinearity, basically of these nonlinear hysteretic links. We want to be able to predict the response of this highly nonlinear and multi-degree of freedom system under seismic excitation for various different parametric configurations, and we want to do it fast. So to do this, we're using a logic for parametric reduction that relies on projection-based methods. What does this mean? It means that we start from the initial equation of the problem of n degrees of freedom. We run multiple simulations from this original problem, and we transform the original equation into a lower dimensional system of r degrees of freedom, much lower than n, that can be derived by using a transformation matrix, basically a Galerkin projection basis, that is extracted from the original simulations of the problem by using an SVD analysis. Again, if this was a linear problem, you would imagine that this would be the model matrix of the system. But of course, here we're discussing a nonlinear, highly nonlinear problem, which, however, even in the reduced representation, retains a structural equation form. This is what gives us here the strength to parameterize in a greater extent, to be able to, let's say, generalize our prediction more easily. So we run the simulations for different sets of parameters. And although this is traditionally done with more naive approaches, where you create clusters of the parameters and different matrices of reduction that correspond to these clusters, we have also proposed a way to do this in a more efficient manner, in a manner that is in a way seamless. It gives you the dependence of these reduced matrices to the set of parameters in a more efficient way. We do this by using, again, the logic of the variational autoencoder. In this case, we use conditional variational autoencoders to reduce the original matrices of the system through some appropriate transformation into let's say, a much lower number of features, a space that can generate these reduced bases that are full matrices, and can do it in an efficient manner, and of course can also do it for a given parameter vector of the problem. And I remind you that the parameters contain both the characteristics of the frame, the material and geometric properties you can imagine, or also characteristics of the input excitation. So by doing this, we now have again a surrogate, but a surrogate that can actually generalize over different sets of parameters. Of course, you see here, for the case of two parameters for visualizing the space, we also have different errors depending on where you are at the parametric space. But in all cases, we try to fashion something that gives us an acceptable approximation. This is also something that the engineer, of course, can regulate. You can decide what is enough in a sense for you. What is an acceptable error, and when you have this, when you have achieved this precision over your parametric space, then you have generated the reduced order model. A bonus that comes from the approach that we're suggesting is that you do not only have a deterministic prediction of the response, but you can also have confidence bounds, and not really confidence intervals in this case, but we can offer error bounds because we have the possibility to use a probabilistic version of the autoencoder. We use this conditional variational autoencoder, which means that we can sample the latent space, and we can generate multiple samples or instances of the response for the same parameter vector. So we can have some sort of confidence on the error in which we can attribute to the prediction. So what I have shown so far is how to generate efficient reduced order models because they're a necessary ingredient of digital twinning, but I have not yet explained how you can connect them with data. And this is what I will now discuss. And to discuss this, I have to present this kind of spectrum, which we suggest is really the space in which the various methods that we have for fusing physics-based data and physics-based models and data exist in. So we have defined here two axes. One axis corresponds to the physics that we claim we are, or that we can claim we know, and the horizontal axis, which corresponds to the data that we have available. Depending on this balance, you basically can view the diagonal of this spectrum as going from a white box approach to a black box approach. And in between, we have what you would call a gray box approach, but we find it more appropriate to imagine it in this two-dimensional representation because it really it is an issue of balance of how you mix these two ingredients, the physics and the data. Now, to describe this mixing, allow me to start from the more white box approach, or rather what is closer to a white box approach, which is what we call the Bayesian filters. Now, for those of you who may have worked with these Bayesian filters, this is a way to merge physics-based models and data, provided that you can convert your physics-based model, which for us is usually a dynamic model, into a state space form. And this is usually the case. Even if it is a reduced order model, we typically can bring it in the state space form. And then we can also link it to the second set of equations, y, which is basically the observations that you get from that system, the sparse measurements you have from certain degrees of freedom. You can see these models either in their continuous or in their discrete form. Usually we use the discrete form. So here I have marked in blue the aspects that are regulated by a model of the system, probably the reduced order model that I explained before. And then on the other hand, we also have the data, which you see here marked in pink or red. And unfortunately, we also have the various uncertainties that are involved in the system, which you see here marked or represented by the various noise terms that may be representing modeling imprecision or measurement uncertainty or the mix of the two. These are the basic ingredients of the Bayesian filtering framework, and the way in which it is resolved for nonlinear problems, which is what we are interested in, is by using sampling strategies. So assume you have a dynamical model of your system, and assume that you have what is called the state of the system. That is basically just a term to denote the displacement and velocities, the states of the system. We assume that these are uncertain and therefore some sort of probabilistic parameter that can be approximated through sampling. And you can use different types of methods for this sampling. There exists the unscented Kalman filter, the particle filter, the ensemble Kalman filter. We will here basically describe all of these methods that use particles as similar. And you can have these particles and propagate them through the dynamics equation of motion of your problem. This will give you the prediction of the response of the system at the next point in time. This is the job of the discrete equation of motion, which may be coming from a reduced order model. And therefore, you have a prior estimate of what is the response at the next point in time. What you're missing is how does this comply with the data that you have at hand? To understand this, we can predict what the measurements we have are. And we can also calculate the discrepancy, basically how much our measurement equation, which gives us the prediction at the locations of the sensors, is different to the actual sensor reading. By using this additional information, you can weigh the contribution of the prediction of the model in the data to get a posterior estimation, which is the final estimation at the next point in time. Now, this kind of modeling, there are aspects of modeling here, both in the first and the second step, and they have to do with the model that you use for the dynamics and the generation of measurements. And this can come from the reduced order model. At the end of the day, the balance of the two, of the data and the model prediction, is actually weighted through a Bayesian perspective, and it is Bayes' rule that we use to obtain the posterior. We iterate this process over time, and then we're able to get the updated response of the system at every point in time, usually often in real time, so as the data flow is attained. In the past years, we have been actually developing these kinds of schemes for various uncertainties to reflect the original problem that I showed you, trying to do everything and everywhere all at once. So for estimating the response of the system, for jointly estimating the response and the parameters of the problem. Sometimes we want to estimate the input, the load to the system and the response, or sometimes we want to do everything together. This can be an ill-posed problem, but under certain observations, it can actually also be a solvable problem if you're respecting certain conditions of observability, invertibility, and so forth. So we have been developing these methods with multiple collaborators also for challenging problems, such as non-smooth problems or problems with distributed loadings. And you can find this actually in a recent paper that we published that is essentially a review of all of these methods. It is a library that is accompanied also by corresponding code in Python for implementing these kinds of Bayesian filtering methods that can allow you to merge physics-based models with data that is dynamic in nature, so for vibration-based problems. Now, the problem is that it's not always very easy to use these kinds of methods. However, I want to show you, first of all, a proof of concept of how you would use this kind of method on a realistic setting, an example from monitoring on airspace structures. Assume we have the fuselage of an aircraft that we here wish to monitor. We have certain sensors that are deployed here in red, and we would like to, first of all, discover in a digital twinning sense what is the response of the system in unmeasured locations, shown here in green, but also maybe what is the damage to the system. And damage can be present on such a thin shell structure in multiple locations, not only one, but various locations, and usually in the form of cracks. Because this is the case, it means that you need to solve a fracture problem, which you can do with any tool you prefer. We prefer to use the extended finite element method, also because it alleviates the necessity to remesh. But this method is also, although faster than conventional methods, is also very slow. So we need to apply here as well reduced order modeling of this kind of fracture simulation problem. And then we need to fuse it with the data we assumed we had available, which we will assume is in the form of accelerations in these 4 sensor locations. And we'll use Bayesian filtering to do this fusion. So we're using reduced order modeling in the sense of what I described before, but now the problem is non-smooth because the parameters of the problem are the different locations of the crack. And in principle, if you were to solve this conventionally, you would have to have a different mesh. Even with the extended finite element method, you would need to have different enrichment nodes to simulate this problem. This would alter the number of degrees of freedom of the problem, which is an issue for generating our basis. So to alleviate this issue, we resort back to our traditional knowledge of structural mechanics, and we use a trick, essentially, mesh morphing, to use a construct that has always the same number of nodes and the same number of degrees of freedom, but can simulate various topologies of cracks within our thin shell curved geometry domain. So we take our initial mesh, which is curved. We use discrete minimal surfaces to convert it into a flat mesh. We use mesh morphing and a reference crack, which is then shifted all over the domain in order to be able to parametrically feature different types of cracks. But we always use the same number of nodes, which gives us the possibility to do the reduction and to produce these reduced order transformation matrices, the basis, that can help us generate a reduced order model of the problem that gives us a dynamic simulation of this cracked domain faster than this video is here rendered, in fact, so that we can couple it with data at feasibly real time. And the coupling with data is done with the process that I showed before. We are using a Bayesian filter to do this because it is a task of input state estimation. So we are claiming that here the input or the load to the system is unknown, because it is not easy to claim that we can measure the load for this kind of system. So it's a task where we have to infer, or at least assume that the input is unknown, then we also need to estimate the response. This is why we use an augmented Kalman filter, because it gives us the opportunity to assume an evolution model for that unknown input. You can even use more elaborate constructs than what I'm showing here, which is a random walk. You can use a Gaussian process, lightning force model, which also colleagues are developing and we have worked on, which is a more refined representation. But at the end of the day, you can have a state space representation of the problem and its dynamics, which is shown here. And additionally, you can try to infer also the parameters of the problem, which here are the locations of the crack and really is the damage detection premise. And we do this by running these augmented Kalman filters in parallel for different parametric configurations and different bases that are generated very, very fast and are running also very, very fast and in parallel. And then by solving essentially an optimization problem, we retain the best performing set of parameters and its corresponding predictions. So we can solve both the damage identification task because by having parameterized the possible flaws, we are able to converge to their correct characterization, the location in the domain and their extent, for example. But more importantly for us, we can also achieve the digital twinning task. We can predict the response of the system at any location other than the ones we measured, other than the red ones. Here I'm showing you the locations indicated in green. And you would see here that the prediction is quite accurate. And the very beneficial aspect is that it is done in fractions of a second for an analysis that is lasting for a nominal 20 seconds. Of course, this is only a simulation, but the point is that we have actually implemented this concept, precisely this concept, the augmented Kalman filter on real systems. And this has been done with partners in Siemens Industry Software. And we had a joint PhD student, Dr. Silvia Vettori, who tried this kind of a concept on a wind turbine blade, instrumented with point-wise acceleration. You can see them slightly here, acceleration and strain gauges that was tested in lab conditions. She used this idea of fusing a physics-based reduced order model. She used substructuring for her reduction and an augmented Kalman filter for the unknown inputs. And she generated a predictive digital twin that can generate the response of the system at its full field. So you can have the displacement prediction and therefore also the strain, if you wish, or elements of the strain at the full field. And this was then, this is something that you can then imagine to render also on an app in a form of information that can be fed to the engineers, who can then proceed to conduct downstream tasks, such as diagnostic tasks that you can have, because you have a predictive model, you can figure out how far this is from expected response. But you can also do prognostic tasks or even tasks that allow you to improve the design of these systems, because now you have a full field estimate of how this system performs. You can even identify hotspots that would require, for example, improvement. Now, this kind of logic you will also see invested in two of the spin-offs that come from our group, which generate this or exploit these kinds of ideas of hybrid modeling and put it into practice on real and actual operating systems. Now, there's one thing, however, that I probably oversold. I don't want to say oversold, but that you have to be aware of. If you have a system that is too far away from the originally assumed response or the original physics-based model that you use, it is not always easy to claim that you can actually simulate such a system, at least simulate it successfully enough to be able to fuse it with data without large discrepancies and without deviating from your predictions. So there exist such systems. They exist because either we are indirectly monitoring our systems, either because we have very complex structures, and we cannot always claim to have a physics-based model that can perfectly capture everything. So when that happens, we have to actually move further down into that diagonal of the original spectrum that I showed you. We have to embrace learning more from data, and we have to abandon our reliance on the vertical axis, which was the physics. You will find a summary of different methods that you can use for this that we have also experimented with in our recent paper that appear in Data-Centric Engineering, where you see both the paper and the code for trying some of these methods, at least those that we have depicted on this spectrum. So I will show you such a concept here. for the case where we wish to infer models for more complex systems, and physics is just not enough on its own. Now, the black box way to do this, so if I was to go back, if you're here at the very bottom right side of the spectrum, where you only rely on data and not at all almost on physics, it is possible to also do that. So we have methods to do that in the more or less the Bayesian filtering context. So again, you can have a state space of a nonlinear system that can be inferred purely from data, and where you can actually learn the functions f and g that describe the dynamics of the system and the inference of the observations. This would be the transition, and this would be the emission model. The so-called deep Markov model, which is basically a temporal variational autoencoder, can do this job. It can infer as a black box nonlinear functions in the form of neural networks that can actually give you the dynamics that would reproduce your data. And they do this by minimizing a certain elbow function, basically a certain objective function that tries to match the fit of the data to the prediction. The problem with these kinds of methods is that the latent space that they recover has no physical meaning. So really all that you're able to reproduce is what you measure. This is what you can reproduce that is physical. The rest, the latent space, is useful for feature extraction, but not for digital twinning, which is a primary interest of ours. So the generalization capability of these approaches is actually quite poor. Instead, what we would like to do is to move a bit further up from that bottom right spot of our spectrum and to, let's say, seed in some physics-based knowledge in order to boost the generalization capability of these kinds of models, even though we cannot claim to know the whole physics. So let's see how we can do this. There's a different array of tools that you can use that you can actually classify in so-called physics-guided, physics-encoded, or physics-informed schemes. The difference is the way in which you use the physics into your model. If it is explicitly fused into your equations, then you would call it a physics-guided scheme. If it is encoded in the structure of your neural network, for example, because your network is a neural ODE, so on its own, it acts as a differentiator, or because you're using a symplectic encoder, so you have something that is respecting Hamiltonian principles, then this is a physics-encoded scheme. Or if you're loosely adding your physics as a constraint in the objective function, which doesn't necessarily have to be strictly adhered to, then this is a physics-informed model. You see here different members of our groups working on these schemes, and I'll show you the scheme that I think is a good description of how you merge the two. So we have recently proposed the so-called physics-guided deep Markov models, where we take the previous black box that I showed, the deep Markov model, which is a purely learning-based model from data, and we fuse part of the physics of the system that we know, even though it's not perfect. You can imagine to fuse something that is a linear model of your system, even if the system is nonlinear. And you're saying that even though I know that I'm not perfectly capturing the physics, I can learn the rest, what remains, the error maybe that remains from the data that I have at hand. So you have this kind of a superposition in this case that tries to capture or complement your model, but the benefit of using even the partial physics is that the recovered latent space is actually interpretable and actually exploitable for digital twinning purposes. I won't go through the details of this because you can see them in the paper, but I will show you an example of first of a very simple system, a pendulum that is a simple yet is a nonlinear system. For this example, we're assuming that we have video data, which are basically a series of images, therefore encoding the angular position of the pendulum. And we assume that we're trying to help the identification by assuming that we also know a linear model of this pendulum system. And we use our physics-guided deep Markov model, and the result is what you see here. We can actually very well approximate, even if it's scaled, a very good version of the latent space of the system. So we have the phase space plot that would really correspond to this system. Whereas if you try to use the purely black box approach on the right, what you would faithfully recover is the angular position, because that's what you're observing. But the system has no obligation to learn the further physics-based quantity, which is the velocity, the angular velocity. And because it doesn't have this obligation, your recovered latent space is actually irrelevant to the physical one. And this is not a failure of the algorithm, because it's simply not the task of this algorithm to infer your physical latent space. But for us, this is what is necessary, and this is what we need to do to be able to predict responsive systems, even in locations that are not measured, given that we usually only measure in very sparse locations. We try to implement, of course, these principles not in the simple example I showed you before, but on real problems. And one of these problems is drive-by monitoring, which we try to do by instrumenting both cars and trains, and trying to do this with relatively cheap sensors that give indirect information on the response of these systems, such as acceleration, from which we're trying to infer the condition of the system. We do this both in Singapore and in Switzerland with appropriate partners. And I show you a bit here of that principle. Usually we have instrumented vehicles where we can have a simplified model that is not perfect. So we assume we have half car or other type of model of the vehicle, and we complement it with learning, with a learning term. And we show that actually, if you do that, you can infer quantities of interest, such as the roughness of the pavement of the road that is being traversed. And you only can do this optimally when you have a good mixing of the two. Now, this mixing of the two is not something that you have to force. This hyperparameter of the mixing component is actually something that can be learned by the system. And we have been doing this also on a real project recently, collaborating with partners in India, the Indian state authorities, and the spin-off from our group, RTDT, as well as an instrumentation company in Switzerland, Kistler, where we have delivered an algorithm for inference of the roadway International Road Roughness Index for new roadways in India using such principles and recorded data from a vehicle. We have been doing the same also for the slightly more complex problem of inferring bridge dynamics, but now using instrumented trains. And this is by Harastura, a member of our group, who is using acceleration information from axle boxes on trains and a filtering approach, such as the one I showed you before, together with a reduced order model, for inferring the model properties of bridges that are being traversed by trains that are actually instrumented. Now, again, I want to skip some of these details that you can find in our paper, but I want to show you that we have implemented this also on more complex systems for corroboration. For example, we have done it on the open source, freely available data for the seismic response prediction of the San Bernardino building. We have used such an algorithm, specifically here, the neural extended Kalman filter, which is again a revised module of a black box general model. It's a model that has principle of dynamics instilled with it. And we show that we can predict the response of this complex building without using much information on the model, but by using some sort of bias that is conducive to the improvement of the prediction capability. We have done it also for a benchmark that we have put out for the community, which is a small-scale blade that we have tested under climatic variability and where we have induced controllable different damage conditions. And we have also done it for an experiment that was conducted where graciously the data was offered by Professor Nagaraja. And here you see it's a non-linear frame with a negative stiffness damping device. And what we did is we pretended that we here only are able to know what is the linear conventional model of the shear frame, and we leave the non-linear response that is induced by the damper to be learned by a neural network. This is a physics-informed neural ODE in this case, which achieves a very good approximation of the overall problem. Let's say here you see the agreement of the improved model that uses this learning term in blue with the original problem, with the original data that you see here in gray. And we can also do it actually quite efficiently, so with a very fast computing system. Now, an additional benefit is that we can also recover what that extra term, the term that was learned from the data is. You can plot this kind of a term and you can fit a function to it, for example, for describing the hysteretic loop that would correspond to this nonlinear damper. You could even go a step further and you could try to use dictionary methods and sparse regressions, sparse symbolic regressions, such as, for example, what is used by the methods in SIMD or other approximations of this. And you could figure out, instead of using a neural network, what would be actually an analytic approximation to this problem. For example, here we approximated it using a polynomial so that we then have a relationship that describes this kind of hysteretic loop that is actually characteristic of the device that is used here. Now, we're very interested in deciphering, what this fitting of these neural network models really means. And this is why lately, in work that has been done together with my colleagues Sid Mishra and Laura De Laurentiis and led by George Kissas, fellow of our ATH-AI Center, we have developed a method that is using symbolic expressions for discovery of material laws in the first work. And now currently we're extending it to discovery of ordinary differential equations. There's not enough time, so I will not go through the details of this. I will just tell you that it's something we're trying to do by using symbolic expressions that are organized in the form of graphs. So we're using the power of structured graphs, trees in this case, to create formal grammars that can actually work together with data and infer representations that, for example, in this case, would be representations that describe constitutive laws of materials, just by using as data, for example, DIC information. So you feed your DIC information, this would correspond to some sort of strain field, and then you try to see if you can figure out what is the symbolic expression and material law that would actually be able to reconstruct this information. For the sake of time, I will not go through the details of this. You can find it in our recently published work, because I would like to show you for a closing what we would like to do next. And what we would like to do next is, first of all, to reach that level of assessing our networks at the ecosystem level. For this, we have been working on using this kind of indirect monitoring approach with instrumented vehicles at a large scale. We do this by also developing our own low-cost, low-maintenance types of platforms. We deploy them on different types of vehicles, not only on cars and trains that are sometimes hard to access, but even on robotic platforms, such as the toy robot that you see here. It's something that we use to traverse the shoulders of bridges in an automated fashion, in a non-invasive fashion. And we use it to collect response information from these bridge systems, which we can then use to derive indicators, usually model indicators of performance, that can then be classified to also explain whether the system is at the expected operation or whether we are actually picking up anomalies. This information is then fed for the decision support of these systems, and we have been working with the Swiss Federal Railways for this. Again, through indirect monitoring, we use data collected from diagnostic vehicles that are traversing different types of railway infrastructure, sometimes even damaged infrastructure that has to do with the deterioration of the subsoil conditions, for example. And we use indicators that come from measurements. Here, such an indicator is the so-called fractal value. And we try to fit evolution models to these kinds of recordings by using historical data. We construct basically an environment of the evolution of this system, and by using information on repair actions and the effect that they have on the system, but also their costs, we're able to devise an optimal strategy that is guided from the observations that we collect from the system, which are, however, uncertain. To deal with this, we're using partially observable Markov decision processes. We use uncertain observations that are indirect, as I showed you, and we're using information that comes from the experts that have to do with their experience, previous logs as well, as to how the system performs when different repair actions are performed. And then we're able to say what would be the optimal strategy to follow within a long-term horizon for best managing these assets in the long term. Now, the ecosystem level is something we're very interested in. And of course, you can imagine that at the wind farm level, this is also very important. And the way in which we found we can best tackle this kind of system level approach is to use graph representations. So for wind farm level assessment, we use graph neural networks to try and simulate these systems, not only for specific configurations that are known, but then also to use our models for predicting new configurations, new designs of wind farms, to which we can attach predictions of important properties, such as the power production in the farm per turbine, for different turbulence intensity levels, what would be the damage equivalent load per turbine for this kind of configuration, and of course use this information to advise the operators on how to best configure these farms given specific site conditions. And it's the power, the extrapolative power of graph neural networks that allows us to do this. I close by just showing you now altogether the vision of what we call augmented digital twins. Augmented because they have these 4 layers where you start from the data, you interpret and you complement with the physics, You bring in the information by the experts so that you can do the complete management over a prolonged time horizon. And then we try to extrapolate to the system level to transfer our predictions to possibly non-instrumented systems at what we call the ecosystem level. So with this slide, I'm going to close, and I would be happy to receive any questions. Thank you very much for the attention.
Yeah, Eleni, thank you very much. Are there any questions from the audience?
So we have nothing yet in the dialogue boxes, but we will give plenty of time for people to formulate any questions or comments that they have.
Okay, Eleni, that was very interesting. I have a question. I know you went through this a little bit, but on the model updating with nonlinearities, I think you described that a bit. How much? I'm very interested in updating models as damage accrues. How much data you need, and to what degree of the nonlinearity can you rely on? I think it's still a developing topic.
Of course. And you have to think of the additional difficulty that we're doing this online, right? So I'm not using an offline method, which, you have a batch of data and you try your best to condition parameters so that you have the full batch. We're really trying to do the best we can for sequential estimation. So it's not easy always to reply to this question, but there are formal aspects that can be used. First of all, your model that you construct and you feed into the system has to be observable. Even for these, even when you're using a learned model from the data, there are rules and ways to check nonlinear observability, which would apply to these nonlinear functions. It also has to be identifiable, because updating means inference of parameters. And there are formal metrics that define observability and identifiability also for nonlinear systems. We have done work together with my brother in the University of Oxford. You will see also from his group a large line of works discussing formal concepts of observability and identifiability, so that you can be able, from your data that you have, to derive the parameters of interest, let's say. But on the other hand, there's also one very important aspect that is non-theoretical so much, because what I said before can be inferred from the equations. There is the aspect of practical identifiability and observability, because your data can be corrupt by noise to a degree where it is not informative. So this as well has to be checked, and there are ways to check it. But if, for example, if you're trying to identify a crack and your sensor is so far away that it will not be affected, by the presence of this crack effectively, then of course there's no chance to be able to solve this problem. This is why optimal sensor placement also plays a role. And this is what actually also feeds into observability and identifiability. We're looking at the locations and the degrees of freedom that you're actually measuring. So the placement of the sensors is key for this kind of recovery.
Okay.
And there's
I had a question,
of course.
Yes, no, that's very interesting. I had a question that evolved as you were talking about. I think you answered, you use reduced order models, and I always, particularly, having come from a background of more civil infrastructure and extreme events, looking at localized damage, and so trying to back propagate from the global response to get to the extent of damage and how localized it is. When you use your reduced order models, are you able to what degree can you? I'll just call it back propagation. I'm not sure it's the right words.
Yeah, this is a very good question. So there's different types of reduced order models. If you choose to use a reduced order model that is merely a surrogate, but a surrogate that can only reproduce response at the global level, oftentimes there's no way to go back into the very fine details of a strain, a localized strain into the system. This is why we have proposed this approach that I showed, and I can now project again as projection-based ROMs. And the reason why we use these is because at any point in time, we actually also have to go back to the fine coordinates. We're solving and we're using hyper-reduction. So we're always connected to the original degrees of freedom, and we're always able to recover even the strains of a finely meshed geometry. We can always recover it for every point in time. And we're doing this exactly because oftentimes we're interested in localized phenomena. So the global properties of frequencies or modes are simply not enough in this case. So you need to be able to link into that localized nature. And so here it plays a role. What is the reduction strategy? If it's purely a model approximation, maybe you will never be able to recover it. If it's something that allows you to go back to the strain, to the original degrees of freedom and their displacement, and therefore the strains, recovered through either a linear or non-linear solution problem, then it's possible to do that.
Okay, there's a question in the chat. Do you want me to read that to you?
You guys can go
Chatzi,
through that on your own. Yeah.
I can read that to you. So actually there's two now, but so I think I kind of opened up the floodgates here for questions. Sorry, but hello, Professor Chatzi.
That's very nice.
Nice presentation.
Yeah.
What are your thoughts about the scalability of the gray box models like PG, neural network S?
Yeah.
How well do they scale to structure with multiple degrees of freedom, word
A very
responses
good,
coupled, etc.?
A very good question. And again, this is where I will argue that by just using black box models, you're actually never going to be able to recover the very fine-grained response at multiple degrees of freedom. It's going to condense a lot of information. But if you use a structured physics-based model of the system that is of reduced nature, they can always recover the response at the original degrees of freedom, which is here what we basically advocate for. Then you can tackle this higher order nonlinearity. Of course, it is always conducive to solving the problem when the whole, imagine you have a large scale system, if it can be, at the end of the day, represented by few latent features, in other words, by few nonlinear normal modes, then it is easier to learn and solve. When you have a highly dimensional nonlinear system where also the latent space cannot be really compacted, then suddenly it becomes very hard to solve. And different strategies can be used. We use substructuring to better tackle this problem. So we isolate structures, we treat their boundaries and the inputs to the boundaries as unknown inputs, and we can more easily solve the problem in that case, provided that we have sensors in the substructured area. This kind of logic is also very useful for hybrid simulation, because you can imagine that the substructure is the tested component, for instance, and then it's easier to actually tackle the solution of the problem.
Yes, so, well, in fact, yeah, you mentioned hybrid simulation. I think that's a very interesting idea about combining the two, because we have physical data we're acquiring in real time that could be used to update
Exactly, and imagine that your numerical substructure is something very big usually. You have to reduce it typically to be able to feed it maybe in a control loop. I don't know if it's pseudostatic, things are easier. If you have a real dynamic system in the loop, suddenly it becomes quite important to have a reduced model.
Yeah. Now, there's another question associated with evaluating the uncertainty of predictions and just the mean value. I think what the question really relates to is the variation of coefficient variation or the scattering. How is the prediction achieved when you evaluate the model?
No, I'm not sure what this question is referring to. Maybe it was referring to the situation where I showed our prediction and then I showed the error bounds. I think this is probably what it means. In that case, you have to think of the fact that we were assessing the reduced order model and only in forward simulation. I hadn't yet coupled it with data. So the way in which we try to value efficacy in that case is to try and compare it to the original model as well. But the way in which we try to quantify the uncertainty is indeed by sampling. So because a reduced order model is generated from a latent space that is described as a random variable, we generate many samples from that latent space for a given parametric configuration. From these many samples, we have different realizations of these reduced matrices, and we run in parallel simulations, full dynamic simulations, and that's how you see the constructed error bounds. These are the envelopes, the max and minimum. And the mean, because it was a good question, the mean is actually the simulation of the median. It's not the average simulation. So it's a full simulation of the median sample, let's say. But there are different ways to treat it, to approximate it.
So there's an interesting question that follows that I actually was thinking myself. You showed a graph there that had a time had the mean plus or minus 2 standard deviations, which is like what the 84th percentile, or almost the confidence interval is about 5%. So here's the question. Is the assumption that the estimated
Over
state of
Gaussian.
likelihood follows a Gaussian distribution.
It's
What
not-
if we
it's
don't
not
know
in-
the actual
yeah.
distribution?
This is the point. That's why I want to refer to them as error bounds, which is more appropriate. It's not entirely correct to say it's a Gaussian. You have to show indeed that it is a Gaussian from the many simulations, and you have to show over time that it more or less has the profile of a Gaussian, even if it has different sigma, that's fine. It should still have the profile of a Gaussian, and that's not always respected. So instead, in more recent work, we have replaced this with the maximum and minimum and not 2 sigma, because it's more appropriate, in fact.
Okay. Let's see, any other questions here? We had an onslaught of some, but
There's one in the Q&A I'd like to get to. If you want to read it, I'll read it from Lewis Lynn. Do you think there's a limitation for data-driven models because of the sensors we use? And then the second part is, how do you think we can develop measuring different forms of physics, or should have to rely more on simulations as training data?
Yeah, of course, this is a very good question, because we're always, okay, we say we have new and lower cost sensors, but they're always going to be limited, especially when you want to have localized phenomena. I mean, you cannot imagine to densely instrument the whole set of your structures. And that's why I imagine physics as a way to complement this, this handicap that we have. I don't think we need to rely only on simulations. And that's why in the frameworks that I showed you, usually the data in the model are running in the loop. It's not that we are using training configurations where you're only run on simulations. Maybe in some cases when you want to perform the reduction, but it's essential afterwards that this reduced model also lives with the data. Otherwise, it's still, in my opinion, not enough to just purely try to train on simulation and then try to predict on another domain and hope that you're doing well. I think that it's imperative to have some measurements, even if they're limited, even if they are sparse. I believe that they have tremendous information to offer for correcting the inherently flawed and approximative nature of our models. And so for me, it's important to always balance the two and try to use them in tandem.
Chatzi, I have a question. I guess we can go on forever, but I don't think we don't want to keep you.
No,
when
I'm
you have
enjoying the discussions.
the neural networks, I mean, typically, I guess I just call it this, although you could think of it maybe differently, but usually they're trained in an open loop environment, input and output, and you try to in the conventional way optimize the weights
not
necessary.
necessary, yeah. But not in what I showed you. So in what I showed you, they're following the Bayesian logic. So actually, if not at every point in time, in some cases in windows or batches of data. So we try to do it online. That's why we call them temporal variational autoencoders. And the logic is that indeed you have sort of the observer logic, which is very important for us. So the prediction, but also the correction by the observation.
Yes, but well, the reason I ask is we've worked a little bit with these, and we do this with cyber physical simulation, which the neural network then becomes part of a closed loop system.
Exactly, it is a closed loop.
But so if you train it for open loop, you can get overfitting issues. That is the coupling with the integration scheme and the rest of the structure, and so I guess what you're suggesting is the approach you looked at would try to avoid, I guess, quote unquote, the overfitting issues.
Exactly, you put it very nicely. I'm advocating for a closed loop approach. That's actually the way to put it. Because the open loop approach, or what I refer to as forward modeling, can easily drift, can deviate, can go into
and I guess it's more sensitive to what I quote unquote extrapolation. I mean, it sees data it's never seen before. It tends to go a little bit berserk there.
Exactly. Whereas if you still have some way to correct it, it can still be in, let's say, tolerable prediction bounds.
Okay. Well, very interesting. Let's see. Any other questions from anyone?
All right, so
no questions.
I think chat. I don't know if you kept up with the chat. If you want to read it.
Let me move down a little bit here, Tommy.
I guess it's the last one. Does the PGNN method take more compute? Of course, I showed many methods. I guess you asked on the physics guided deep Markov model. And it says, does it take more computational cost than deep learning, than the pure deep learning method? Yeah, I mean, slightly, because you have to think of the fact that there is a reduced order model in the loop, but it's still quite fast to compute. And you also have to think of the fact that there is, you know, you can actually train this kind of model. You can even, in fact, imagine it to use it in an open loop afterwards, after it is trained. But provided that you still want to use it in the closed loop, it will be slightly slower than the pure black box approach, but still not prohibitively slow.
Mm.
Because we made sure to not feed the original FEM, we feed the reduced order model.
Mm. Very, very interesting. All right, let's see. Well, another question here. Does the PGNN method meet with overfitting issue, or can it learn any kinds of complex structure very well? I guess it comes back to the overfitting issue.
Yes. No, I have to say, and I hate it when people do this, but there's no panacea, right? Depending on the problem, you have to choose the right method at hand. That's why we also don't have one method we use. I showed you a spectrum of various options. For instance, if you have very complex structures that are far away from the physics-based model, I would go with the more relaxed framework, which is the physics. For example, for us, it was the physics-guided, excuse me, the neural extended Kalman filter. It's a bit more flexible than a purely physics-guided model that explicitly uses a ROM. Or in other cases, you may want to use a pin. I try to avoid using pins because they can be very, very slow, especially for multidimensional problems. So, you know, depending on what the dimension of your problem is, how far your model is from the actual situation you're deriving data from, you would have to appropriately select also a different scheme. I don't think you can advocate for one PGNN method that solves all. It's very similar to optimization methods. There's no free lunch also here.
I have another kind of general question, because I noticed you have a fairly nice sized research team. What is, I think the audience may be interested in this, what is the background? What kind of person do you look for to add to your team? I mean, there's, you know, obviously structural ophthalmology means you need to have some knowledge about structural mechanics and structural modeling. However, you got to be sort of what I call computer savvy. You know, you can't use computers as a black box. You have to know how to program and code and debug and interpret.
Precisely, you know, the fact that we deal both with physics and with data means that also our team members have to have these competencies, but not at the same time. We never ask this from all. So members of my team have diverse backgrounds as well. We have both civil engineers, mechanical engineers, let's say you can consider them relatively close, but we also have electrical engineers, applied math background, physics, and materials even. Each of which has their strength and is dedicated to a task that best represents their aptitude, but they're all in interaction and there's complementary or joint work where this is needed.
Okay, well, no, very, very, very interesting to hear there. So, any other questions? I think I've probably asked the most, but I'd like to make sure. Okay. Well, Eleni, and I hope I didn't mispronounce your name. I apologize.
No, it's very common. My name is it's not, it doesn't sound like it's red, so you already did a good job.
Okay, I got to be sure I put the accent in the right place. Otherwise, my auto coding is not working. Anyways, no, I appreciate very much first your participation, and the audience does too. So I'm gonna clap, and hopefully the audience will do the same, because I think it was an excellent presentation. It was pretty well attended, and we archive the presentations for people to see. And you know, I encourage any follow-up questions. Perhaps they can contact us. We can forward it to you, or they can contact you directly.
I'm glad you say this, and I would have asked for the same. I think it's easy to find my email online and directly shoot me a question on anything that may seem of interest. We welcome this very, very much.
Yeah.
And also thank you for the invitation. And this
it's our honor to have you here, and you know, and like to invite you as well as anyone in the audience. If you're ever near our facility, you're very much welcome to come and visit, and even come to a research or workshop.
I think it's long overdue. I'm very interested, so yes, I'll try to.
Yeah. So you gave us a lot of references to read when Henry's off to the students. So we'll have to catch up with the work you've done. It seemed like you're really ahead of the curve. You're really leading this field. So look to pay attention to all the things you do here in the future there, and wish you well
We
and
try
moving
to do
forward
good
here.
work, always in good company, but yes, hopefully
Yes.
you'll find interesting things there. Yeah.
Yes. Okay. Well, with that, I guess we should go ahead and finish the webinar, and we'll wish you well, and thank the audience too for participating.
Thank you very much for the invitation.
Yeah, thank you
and,
everybody for
hope to
joining
see
us.
you.
Yes,
Have a
thank you.
good day.
All right,
Bye.
and now-
Yeah, thank you.
Thank you, guys. Take care, everybody.